Hi, I am Ravi Ranjan and this is my YouTube channel. I am Physics. In this video, we are going to discuss a problem based on electrical energy density. So here is the problem. A point charge Q is located at the center O of spherical uncharged conducting layers provided with small orifices as shown in figure. What amount of work has to be performed to slowly transfer charge Q from point O through the orifice and into infinity? So in this diagram, we can see there are two spherical conducting layers, and the first one has inner radius A and outer radius B. The second one has inner radius C and outer radius D. They are concentric to each other and their common center is at point O. And these two conducting layers are also electrically neutral. That means the net charge on each of these conductors would be equal to 0. We have placed a point charge Q at the center, and due to which there would be some induced charges on the surface of conductor. So on this surface some minus q charge will be induced, on this surface plus q charge will be induced, on this surface again minus q charge will be induced, and on this surface plus q charge will be induced. So due to these induced charges there will be electric field everywhere in the space. So due to which this Q charge will be interacting with that electric field and experience electrostatic force. So when we move this point charge from one place to another, throughout its journey it will be experiencing electrostatic force. So in order to move it slowly, we need to apply external force which will be equal and opposite of the electrostatic force acting on it. So we have to find out the work done by that external agent in moving it from point O to infinity through that orifice. Now to find out the work done by external agent, we can think of a few methods. One of the methods can involve basic definition of work done by a force. As we all know that work done by a force is equal to F dot dr and the integral of it from initial to final position. And so the work done by the external agent will be F external dot dr from initial to final position we have to integrate, and F external we have already seen that it will be equal and opposite to electrostatic force experienced by that point charge. But the problem with this method is that when we displace this point charge from point O, the charge distribution on the surface of the conductor will become non-uniform, and finding out the electric field due to non-uniform charge distribution is not going to be very easy. So the electrostatic force experienced by that point charge will be very difficult to find out, and hence F external as a function of R will be very difficult to express. So this integration is not easy to calculate for this particular problem. So this method is not very convenient to find out the work done by external agent here. So can we think of some alternate method to find out the work done by external agent? Yes, we can, and that method involves the work energy theorem. According to work energy theorem, the work done by the external agent will be equal to change in potential energy of the system plus change in kinetic energy of the system. Here in this situation, the change in potential energy of the system is change in electrostatic potential energy of system of charges, and delta k, that is change in kinetic energy, will be equal to 0 because the charge is being moved very slowly. So work done by the external agent will simply turn out to be the change in electrostatic potential energy of the system of the charges, and that will be equal to uf minus ui, final and initial values of electrostatic potential energy of the system. Now, how do we write the electrostatic potential energy of such a system? This system comprises of a point charge and certain continuous charge distribution on the surface of the conductor. So there are four layers of continuous charge distribution. So for continuous charge distribution, the electrostatic potential energy can be written as the self energy, that is U self, and apart from that all those charge distribution and this point charge will be interacting with each other. So counting this point charge Q and four layers of continuous charge distribution, there would be five kind of charge distribution, and they all will be interacting with each other forming pairs. And how many pairs we will be able to have here? That will be 5 C2 and that will be equal to 10. So U interaction, the interaction potential energy will be comprised of 10 terms, and U self will also be having 1 for the point charge and 4 for the surface charge distributions. So there will be lot many terms involved here in the calculation of electrostatic potential energy of the system when we use this expression. So it is again going to be pretty hectic, and this method is also not very convenient. So what do? Do we have some alternate method? Yes, indeed we have. Now, electrostatic potential energy of a system of charges can also be obtained using the concept of electrical energy density and electrical energy stored in space. As we all know that the electrical energy density, which is the electrical energy stored per unit volume, is given by half epsilon naught E square. This is electrical energy density in free space. Free space means the relative permittivity of the medium will be equal to 1. In this formula, E is the magnitude of net electric field due to all the charges present everywhere, and epsilon naught is the permittivity of free space. So this formula allows us to find out the electrical energy density U at a point in space if the electric field at that point is known to us. So using the value of U, we can find out the total electrostatic energy stored in a given volume of space. So that will be equal to integral of U dV, and its integral for the given volume. dV is the volume element, and U times dV will be the infinitesimal energy stored in that element of volume. So the integral of it would be the total electrostatic energy stored in that volume, when we will substitute the value of U as half epsilon naught E square and that times dV, and its integral for the whole volume will give us the total electrical energy stored in that finite volume. And also we can find out the electrostatic potential energy for the system of charges using this expression. The electrostatic potential energy for the system of charges will be equal to the electrical energy stored in the overall space. So it will be given by U is equal to half epsilon naught E square dV, and we have to integrate it from 0 to infinity, that is for the whole space. Now, before we begin to solve our problem, let me derive one more formula, that is for the electrical energy stored in concentric space between the distance r1 and r2 from a point charge q. So here in this diagram I have taken a point charge q, and electric field at distance r from it will be given by E is equal to q upon 4 pi epsilon naught r square, and the electrical energy stored in a given volume will be equal to half epsilon naught E square into dV, and we wish to find out the electrical energy stored from R1 to R2, and so that will turn out to be half epsilon naught. In place of E I will be writing q upon 4 pi epsilon naught R square and the square of it, and for the volume element here I am going to take a spherical shell of radius r whose thickness would be dr. So the infinitesimal volume of this thing will be equal to 4 pi r square dr, and we have to integrate it from r1 to r2 to find out the energy stored in this region of radius r1 and r2. So when we will be simplifying this integration, we will get q square upon 8 pi epsilon naught into 1 by r1 minus 1 by r2, and this result we are going to use in our problem. Now we are ready to solve our problem. All we need to calculate is the final and initial value of electrostatic potential energy of the system and subtract them to find out UF minus UI, and that will be equal to work done by the external agent. So let's look at the initial and final situation of our system. So initially the point charge is placed at the center of these spherical conducting layers, and we have already said that minus q charge will be distributed on the inner surface of the inner shell, plus q charge will be distributed on the outer surface of the inner shell, minus q charge will be distributed on the inner surface of the outer shell, and plus q charge will be distributed on outer surface of the outer shell, and all these charge distribution will be uniform. And taking that into consideration, it is easy for us to write electric field in various region. Electric field will be given by E is equal to Q upon 4 pi epsilon naught R square in any region where the conducting material is not present. For example, from R greater than 0 and less than A, that means in this region, the electric field will be given by Q upon 4 pi epsilon naught R square. In the region for R greater than B and less than C, that means in this region, and for R greater than D, that means in this region, the electric field will be given by Q by 4 pi epsilon naught R square only. And in the region where conducting material is present, the electric field will be equal to 0. For example, for R greater than A but less than B, that means in this conducting layer, and for R greater than C and less than D, that means in this conducting layer, the electric field will be equal to 0. This is derived from the fact that the electric field inside the volume of conductor is equal to 0 under electrostatic condition. Now finally, when the point charge is uh, at infinity, it will be having electric field everywhere in the space given by this expression E is equal to Q upon 4 pi epsilon naught R square for all value of R. And this concentric layer of conductor will be, because very far away from the point charge, there will be no longer any induced charge on any of the surface. So this will not be having any effect for the electrostatic potential energy of the system, and all the electrostatic potential energy of the system will only be due to the field of this point charge. So initially, when the point charge was placed at the center of these concentric layers, electric field Q upon 4 pi epsilon naught R square is present everywhere in space except for the region of conducting layers where electric field is equal to 0. So, electrostatic potential energy of the system is electrical energy stored in complete space, which is this term, that is half epsilon naught, and this is the electric field due to this point charge, that is Q upon 4 pi epsilon naught R square, and the square of it into the volume element 4 pi R square dr. Because it is stored in the complete space, we have to integrate it from 0 to infinity, minus energy that was stored in space of conducting layers. For example, the energy stored between A to B will be given by this integral limiting from A to B, and the energy stored in this space, that was half epsilon naught and E square into 4 pi R square dr, and that integral from C to D. So these two terms we need to subtract from overall in order to get the electrostatic potential energy of the system. The first term actually, when we are integrating it from 0 to infinity, so this term would be actually very large. So we are not going to calculate it, and let me write it as simply UQ. This is also the self energy of a point charge. It would be a very large quantity. And the second and third term, we have already obtained an expression for that integral. And the first term will be Q square upon 8 pi epsilon naught into 1 by A minus 1 by B. And the second term will be Q square upon 8 pi epsilon naught into 1 by C minus 1 by D. So this is the initial value of electrostatic potential energy of the system. Finally, when the point charge is at infinity, the electric field will be given by Q upon 4 pi epsilon naught R square everywhere. So, the final value of electrostatic potential energy will be this integral from 0 to infinity, and that again I will write it as UQ. So in order to find out the work done by external agent, like I already said, we will be using work energy theorem. So work done by external agent will be simply equal to delta U, and delta U will be UF minus UI, and we have already written the expression for UF and UI. So let's substitute them here. So UF is UQ and UI is UQ minus these two terms. So when we will be subtracting them, UQ will get cancelled and we will be left up with Q square upon 8 pi epsilon naught into 1 by A minus 1 by B plus 1 by C minus 1 by D. So this is our answer for this problem. That's it.